Hi everyone. In this session we will be covering counting techniques, but just to remind you, up to this stage you should have looked at exploring data, which includes sampling, graphical and numerical summaries, and now at the moment we're at counting techniques. We've already looked at events, and then after counting techniques we will go back and see how it fits into probability and conditional probability. Right, so first of all, again, the outcomes for this session: you have to know the definitions, very important. Then you must be able to identify the three basic counting techniques from word problems, and then you must be able to use those counting techniques to solve the relevant word problems. Now these word problems will include probability problems in the next section as well. Now the motivation for counting techniques is that it enables us to fairly easily, okay, not always that easy, but fairly easily, it enables us to count the number of outcomes in a sample space and the number of outcomes in an event. Now we need those two values in order to calculate probabilities. So that's what this allows us to do. In the previous section on events, we had a look at some events with very few outcomes, and we were able to graph it very easily. However, in general, it's not that easy. We have many outcomes in some cases. Like for example, if you flip a coin 10 times, then the number of outcomes will be 2 to the power 10. So we're not able to draw that. So we must be able to use another method, which will be our counting techniques, to count how many outcomes we have. Now, there's three basic counting techniques, and we'll be doing them in this order. The first one is a multiplication principle, which is exactly what the name says. We'll be multiplying. The next one is a variation on the multiplication principle. We simply introduce a restriction on the multiplication principle, and then we get permutations. Now the main property of permutations, the main characteristic, is that the order of our selection is important. So the order in which outcomes occur is important. Then lastly, we have combinations, which once again is a further restriction. Right, so multiplication principle is the main one, then we have a restriction, and then we have further restrictions for the combinations. Now for combinations, the order of the selection is not important, whereas with permutations it is important, and we're looking at a specific order of things. For combinations, we're simply looking at a group. We don't care about the order. Now these three formulas, we'll be looking at deriving them, and we'll do that by using examples. Now first of all, what does the multiplication principle, or another word, our counting rule, what does it say? It says that if we have an experiment that can be divided up into multiple stages, okay, now that should sound familiar. A multi-stage experiment is best denoted by a tree diagram. So in other words, if we have a type of experiment that can be illustrated by a tree diagram, and N1 is the number of outcomes for the first stage, N2 the number of outcomes for the second stage, and so forth until we get to the last stage, which is stage K, of which the number of outcomes will be K, then the total number of outcomes for the entire experiment will simply be the product of all of those N's. Now to make a bit more sense of it, let's jump into an example. Suppose that this guy wants to get dressed in the morning, and we're looking at different outfits. Now I haven't included any underwear like socks in here. We're just looking at shirts, trousers, and shoes. So he has 3 t-shirts, he has 2 pairs of trousers, and he has 2 pairs of shoes. So how many different outcomes are possible? Well, the experiment is getting dressed. Okay, very important. In this case, our experiment is getting dressed. Now, the number of stages in this case will be 3, because we need to put on a shirt, we need to put on pants, and we need to put on shoes. So those are the 3 stages. So let's see, using a tree diagram, what do we get? Well, first of all, we start by selecting a shirt. So let's say, for argument's sake, that we select the white shirt first. Now we have the white shirt, and let's assume that all other clothes goes with any shirt. Okay, so it doesn't matter which trousers or which shoes, it all goes together, so we can have any combination of clothing. Right, so we start off with the white shirt, and now if we have the white shirt, then from there we can select our 2 pairs of pants. If we go to the yellow shirt, then we have the same situation. We can select any one of the 2 pairs of pants. If we select the red shirt, then again, same situation. Any one of those 2 pairs of pants. Right, now, let's say we stick with the white shirt and we stick with the blue pants. What happens next? Well, next we need to choose the shoes. So we can choose either sneakers or boots, but the important thing is we have 2 options available. Now in total, if we count these, it adds up to 12 possibilities. But as I said earlier on, this is fairly straightforward because we can construct a tree diagram. But in general, we won't be able to do this. So how do we calculate 12 from the information that's given? Well, if we have a look at the pairs of shoes, okay, that's what we end with, so I'm going to start with that. We have 2 pairs of shoes that go with 1 pair of pants. Now if we increase to 2 pairs of trousers, then there will be 4 pairs of shoes. So basically what it means is that whatever happens here is simply repeated over here. Okay, listen carefully. Whatever happens with the first pair of trousers, the same thing will happen with the second pair of trousers. So whatever we have here is going to be repeated for the second pair. Okay, so that means that this happens 2 times. So we get 1, 2, 3, 4 outcomes, because it's 2 times 2. Now, if we have a look at overall, if we have a look at this entire branch now, okay, because we just looked at these 2 and then those 4, but if we have a look at this whole thing now, we just said that to get the number of outcomes for that, it'll be 2 times 2. But now what happens with this entire set of branches over here? It is simply repeated for the different color t-shirts. There's nothing new that's being added, there's nothing being taken away, so nothing happens to it, it just stays the same. So that means this, whatever we get over here, is repeated 3 times. So we multiply it by 3. So that means that the number of outfits will be 2 times 2 times 3, and that gives us our 12. So that is what is meant by this explanation over here. The 2 will be our N1, this 2 will be our N2, and that one will be our N3. The number of outcomes for each stage multiplied together will give us the total number of outcomes for the experiment. And let's have a look at another one. Now I trust that everybody is familiar with these combination locks, where it's the little wheels inside and you have to roll them until you get the right combination of numbers to open up the lock. It says consider the following combination lock with 3 slots. Okay, these are the 3 slots, 1, 2 and 3 slots, and 10 numbers per slot. So that means on these wheels we have the numbers starting at 0 and it goes all the way around the wheel to 9. And the same with the other 2, they're identical. Now the question is, how many codes are possible? Well, what does the multiplication rule says? It says that if we can take the entire experiment, okay, the entire experiment in this case is getting a code. If we can take the entire experiment and split it up into smaller parts, then we just take the number of outcomes per part and we multiply it together. So if we just quickly look at a tree diagram, then for the first part of the experiment we have 10 possibilities because it's the digits 0 to 9. So there's 10 possibilities for the first stage in our experiment. For the second one, there's also 10. So that means each of these will have 10, each of them. And for the third part, there's also 10. So that means each of these will have 10. So you can see that it becomes really impractical to draw. So what we'll do is we'll identify the 3 stages. We'll see how many possible outcomes we have for each, and the number of codes will simply be the product of those 3 values. That will just be 10 times 10 times 10, which gives us 1,000. Now this 1,000 we should have gotten just by using a bit of common sense. We have 3 identical slots over here, each one with the digits 0 to 9. So the smallest number we can make here will be 3 zeros, the largest one will be 3 nines, and that'll be 1,000 numbers in total. Okay, so that's where this 1,000 comes from. Right, now let's extend this. Now we have 10 slots and 10 numbers on each. So previously we had the first 3, now we've got 10. How many codes are possible? Well, the multiplication rule stays exactly the same. It says find a number for each one, and of course we have to do it for all of them in between as well, and just multiply it all together and we get 10 to the 10. Right, now let's add a restriction. Let's say the same situation, 10 slots, 10 numbers per slot. How many codes are possible now if you may not repeat any numbers? So that means for the first one we'll have 10 possibilities. We can choose any of the numbers 0 to 9. We have the digits 0 to 9. But whatever we choose here must be excluded from the selection in the next one. So that means there's only 9 that's available for the next one. The same thing applies now. For the third stage of this experiment, there will only be 8 possibilities, right? 8 possible outcomes, because we've already used 2 outcomes in the first 2 slots, or the first 2 stages. So if we carry on in that way, you see that the number of options decrease until the very last one, where we only have 1 possibility left, because the first 9 over here all have different digits, and on the wheel we have 10 digits, so that means there's only 1 digit left that we must use. So the multiplication rule still holds, multiply it all together, and we get 10 times 9 times 8 times 7 all the way down to 1. So it's still the multiplication rule, however we've got a restriction, no repetitions. And because of that restriction, we change our notation a bit. We write this as 10 with an exclamation mark. Now this notation 10 with an exclamation mark means 10 factorial. And when you see something like this, any number with an exclamation mark next to it, it means that you'll take that number and you'll multiply it with all the integers below it down to 1. So that's our definition. We have n things to choose from. We need to choose all of those things, but we're not allowed repeating. So that means we'll take n for the first and then the next one less, all the way down to 1. So that gives us our n factorial. Please note that by definition, okay, this is a definition, 0 factorial is 1. Okay, there's no proof for this, it's just a fact that we need to accept. Now let's have a look at another example, but this time we will place another restriction on our multiplication rule. Now before we look at the explanation here on the left, let's just look at the example. Again, consider a combination lock with 3 slots and 10 numbers. How many codes are possible if you may not repeat the numbers? Okay, so we have the 3 slots once again, 10 numbers on each. We may not repeat. So that means for the first stage of the experiment, we have 10 possible outcomes, because we can choose any one of 10. For the next one, we'll have 9, and the next one we'll have 8. So by the multiplication rule, this will be 10 times 9 times 8. Now, you'll see that I've written it in this way over here, 10 factorial divided by 10 minus 3 factorial, because this calculation over here is called a permutation. And the way in which we denote it will be 10 with a capital P and a 3, which means 10 permutation 3. So that means that we have 10 objects to choose from. We must choose 3, and the order is important. So it's 10 permutation 3. Okay? Just to stress that again, the order of the selection is important. So you can see that it's still the multiplication rule, however we have a restriction on it now. Right, let's have a look at another example. Consider selecting a class president and a class secretary from a class consisting of 400 students. How many selections are possible? Well, clearly these are two different positions. Class president does not perform the same tasks as the class secretary. So we can't just choose any two people and say that they are the same, that we now have a group of two. Okay, here are clearly distinct positions. So the selection order matters. Let's compare this to the combination lock. We'll have two slots, okay, slot 1 and slot 2, because we have two positions, the class president and the class secretary. Now for the first position, we can choose any one of 400 students. So let's imagine that there's 400 numbers on this first slot. Now once we've chosen the class president, we cannot choose that person again. So that means for the next selection we only have 399 available. So the number of selections, or the number of permutations, will be 400 times 399. And that, in our notation, is 400p2. 400 to choose from, permutation, because the order is important in which we select those two. Now, this method, or this calculation, might seem a bit confusing, and this one might seem a bit easier. However, it sometimes happens that there are just too many here to list in a practical calculation. So we don't use this, although it is a bit easier to comprehend. We'll rather use this. So you have to get used to this notation. But as I've shown you, it doesn't matter what the type of problem is. If it's a permutation, we can always compare it to the combination lock. The idea is exactly the same. Right, so permutation, the order is important. Now, let's consider selecting a group of 3 letters from the letters A, B, C, and D. How many permutations are possible? Well, we need to choose from 4, so that's the N. We need to choose 3, so that's the R. The order is important, so that means N permutation R. We have 4 to choose from, and we have 3 that we need to choose. So that gives us 24. Okay, if you have a look at the calculation for permutation 3, you can do it on Excel or on your calculator. If you have a look at the result, you'll see that it's 24. Now if we list it, then this is how it will look. We will have to choose 3 from there. So if we start off by choosing ABC, right, we choose ABC, then that's one permutation, or one way of arranging the letters ABC. We can arrange it as ACB, BAC, BCA, CAB, and CBA. So that's just for the first 3. Now we can choose another 3. We can say A, B, and D. Okay, so A, B, D. And how many ways can we arrange that? Well, the same, 6 ways. Now if we look at those arrangements, then it's the same letters in there. So although the arrangement is different, the group of letters is still the same. Okay, from there to there, the group of letters remains the same. It's ABC, it doesn't change. And if we look at each row, then we see that it is the case for each row. Right, the group in each row is the same. So for a permutation, all of these are considered different because the order is different, and think of it in terms of a combination lock. Okay, for a combination lock, the order in which you enter the security code is very important. If my security code is 1234, the lock will only open if I enter 1234. It won't open if I enter 4321, even though it's the same digits. But here, we're simply looking at whether it's the same digits or not. If it's the same digits exactly, we'll just say that's one group. Here, all of these 6 have the same digits, so that's one group. All of these 6 have the same digits, so that's another group, and all of these 6 have the same digits, so that's another group. So out of the 24, we only have 4 groups. Now these 4 groups we call combinations. Now if you can recall from the definition that I gave in the beginning, combinations we use when the order is not important, when we simply select a group of items or objects or elements, whatever you want to call it. So in this case, we have ABC, the order is not important, so we don't count all of these different arrangements or all of these different permutations. Now what you should notice is that we have 3 distinct elements in here. And how many ways can we arrange 3 elements without repetition? Well, according to our multiplication rule, it'll be 3 factorial ways. It'll be 3 for the first position, then there's 2 left for the second, and only 1 left for the last. So in this case, these 3 can be arranged in 6 ways. These 3 in 6 ways. These 3, 6 ways, 6 ways. Now the reason I'm looking at that is because I want to try and figure out how do I go from 24 outcomes, right, 24 permutations, right down to 4 combinations. Well, if I take 24 and I divide it by 3 factorial, which is 6, then I get 4. And that is exactly what a combination is. It is simply a permutation. Okay, for the combination, I'll take the permutation that I have, and I'll divide it by the number of ways in which I can arrange the individual elements. So here I can arrange the individual elements in 3 factorial ways. 3 factorial, but because each one is 3 factorial, this will simply be 3 factorial, and that gives me my 4C3. Obviously, the C stands for combination. Now the way in which we write it is usually this way over here. It seems like a fraction in brackets, but it's not. We don't have the line in between. We simply write at the top the number of elements we can choose from, then we write the number that we will choose, and we put it in brackets. Okay, the other way of writing it is this one over here. This one is not really necessary unless you're going to do calculations in which you want to manipulate the values. Right, let's have a look at another example. These things are best learned through examples. Right, it says here, consider selecting 2 students to help me collect assignments in class. How many selections are possible if the class has 400 students? Now here, there's clearly no distinction between these 2 students. In the previous one we had a class president and a class secretary. Here we only have 2 people that will perform the same task, and that is collecting assignments. So the order in which we select them doesn't matter because they both are equal. They both perform the same task. So because the order doesn't matter, okay, the order is not important, we'll have 400 combination 2. The 400 will be that we can choose from, and the 2 will be what we choose. So 400 combination 2 on our calculators or Excel, whatever you use. Remember, we can write it as 400 permutation 2 divided by 2 factorial. Okay, because we're taking every pair of 2 students, and that 2 people can be arranged in 2 times 1 ways, which is 2 factorial. So we'll divide by 2 factorial, and that will give us our answer of 79,800 possible combinations, which is quite a lot if you consider that the class size is 400. Right, now lastly, we will extend on our combinations. Before we look at the definition, let's just look at the example. It asks how many arrangements of the letters of the word statistics is possible. Now, if we look at the word statistics, we see that it contains 10 letters. Okay, 10 letters. So if we want to arrange those 10 letters, then the number of arrangements will just be 10 factorial. Now remember, 10 factorial is 10 times 9 times 8, 7, 6, 5, 4, 3, 2, and 1. So this is saying we have 10 to choose from for the first position. Then we have, and let's say we choose a T, then we only have 9 left for the second position. We'll take out whatever we choose next, and then only 8 right down to the last one, which is 1. However, there's something we should notice here. If I choose this T for the first position, or whether I choose this T or this T, it doesn't really matter because it looks the same. It's still going to give me the same word, regardless of which of these T's are in the first position. So let's go through and see how many repeats I have. Now, you'll see here, again, lowercase n, because that refers to a number of objects. Subscript 1, because it's the first object that I'm looking at being repeated. So the letter S is being repeated 3 times. So let's suppose that I give each of those S's a subscript so that I can distinguish between them. Now the question is, in how many ways can I arrange these 3 S's? Well, that'll be 3 factorial, because for the first position I will have 3 S's to choose from. Once I've made my selection, let's say I chose that one, then I have 2 to choose from for the next, and let's say I chose that one, and then there's only 1 left for the last position. And so it's 3 factorial ways in which I can arrange those 3 S's. What about the T's? Well, there's 3 T's, and how many ways can I arrange them? In 3 ways. There's how many A's? There's only 1 of them. Okay, so in how many ways can I arrange that? Well, 1 way only. It is where you put it. Next, we have the I's. So there's 2 of those, and how many ways can I arrange 2 I's? That'll be 2 factorial. And then lastly, it seems like C. There's only 1 C, so how many ways can I arrange that 1 C? That'll be 1 factorial. So if we look at the number of ways in which we can arrange all 10, then we can say that it's going to be 10 factorial. However, as I pointed out, these 3 S's will still look the same, doesn't matter in which order we put it. The 3 T's will still look the same regardless of the order. So that makes it so that this is not a permutation. If we do this, if we look at what we did with a combination, where we had to divide to get rid of the number of permutations and only get the group, then we do exactly the same over here. We have to divide by 3 factorial to get rid of the duplicates of the S's. We have to divide by 3 factorial to get rid of the duplicate T's, and the same with the I's. We have to divide by 2 factorial for the I's, and that's exactly what we do over here. So we have our 10 factorial divided by all of these, but please note we don't have to divide by 1 factorial and 1 factorial, because that simply is equal to 1. Okay, it's not going to affect the result. So important to note, where we have identical objects in an arrangement, we count how many of those objects we have and we divide by that factorial, as you can see from the steps that I've followed. Right, so in conclusion, we've looked at the multiplication principle, where we simply take the different number of outcomes for the different stages of the experiment and we multiply together. We looked at permutations, which placed a restriction on the multiplication, and combinations, which placed a further restriction. Permutations will be where the order is important, so you can think of that like the combination lock. Combinations will be where the order is not important, so that will be the permutation divided by the number that you select factorial. You can see here, that's my permutation, so that's my permutation, and I divide it by r factorial, which is the number that we select. Right, this section is important. We're going to be using especially combinations in the following chapters when we look at random variables, so please practice this. It is also important for probability calculations in general, and there will be a few questions on this, not just in this section, but also when it comes to probability calculations. So please practice this.